Now that we've learned about identities, let's start solving some trig equations. So, difference between identities and equations. Identities are true for all of the inputs. Equations are only true for certain inputs, and our goal will be to find them. We'll want to find all of the solutions, and then we'll want to find the solutions that just live on one trip around the unit circle. Oops, so there's our learning objectives. Let's make this a little bigger. Nope, doesn't work. And we can't see the whole thing. So, intro example. Determine solutions on the interval from 0 to 2 pi of 2 sine theta plus the square root of 2 is 0. So first thing we would do is write it down. So 2 sine theta plus the square root of 2 is equal to 0. Just like a linear equation, if you had 2x plus 3 equals 0, the first thing you would do is to subtract from each side. So we're starting to isolate the trig term. So first thing you do is get that plus away from it. Then we get this 2 coefficient away from it by dividing. Then we use our knowledge of the unit circle. Square root of 2 over 2. Well, we know that sine and cosine are both square root of 2 over 2 when you have 4 in the denominator. So that's what I meant to write here. So here at pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. But we want it to be negative, so the negative answers live down here below the x-axis. So theta is equal to 5 pi over 4 or 7 pi over 4. Now we don't have to think about domain restrictions because we're seeking specific solutions. So if you wanted to think about taking the inverse or arc sine of each side, you don't have to think about getting an answer that lives on the right-hand side of the unit circle because we're looking for answers that live in the interval from 0 to 2 pi, so a whole loop around the unit circle. Now, if we want all the solutions, we use our answers on one loop around the unit circle as a guide. And think about the period of sine. So theta could be equal to 5 pi over 4 plus a loop around the unit circle, plus a loop around the unit circle. So plus 2 pi times, okay, we're using k. Sometimes you'll see k, sometimes you'll see n used. Or theta could be equal to 7 pi over 4 plus 2 pi k. First we find the solutions between 0 and 2 pi, then we find all the solutions. So, let's try another one. Our first real example. We have square root of 3 times secant of theta equals 2. So first thing I'm going to do is divide both sides by the square root of 3. Now, maybe you're really familiar with secant and you don't mind working with it. That's fine. You can answer your question from here. If you're a bigger fan of sine and cosine, I would rewrite this as 1 over cosine of theta is equal to 2 over the square root of 3, which means cosine of theta is equal to the square root of 3 over 2, and that's something I can just read off my unit circle, and I like that. Yeah, by the time you do them all, you'll look at this and say, secant equals 2 over square root of 3, so cosine is square root of 3 over 2. And then I go back and think about my unit circle. Cosine is square root of 3 over 2. Everywhere that we're further from the center from side to side than we are tall. So that's a pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. So we just have to figure out which ones are positive. Well, cosine is positive over here. So we have theta equals 11 pi over 6, or pi over 6. I don't know why I put 11 pi first. I want my smaller one first. So pi over 6 and 11 pi over 6. Period is 2 pi. So theta is equal to pi over 6 plus 2 pi k, or, and I'll just use a curly bracket like we did on the last slide, 11 pi over 6 plus 2 pi k. There's our pretty answer. So, now you're going to practice some. These are problems that you can get just by looking at your unit circle. So try to do them that way because you know you're not going to have a calculator on test 2. So how did they go? Started with cosine is a half, so that one was all ready to be solved. All you had to do was look at your unit circle. Cosine is equal to a half when you have 3 in the denominator. So I went ahead and put all of the 3 in the denominators, and then I circled the one where cosine is positive. So pi over 3 and 5 pi over 3. And then all the solutions will be 2 pi intervals of that. So every time you loop around that unit circle again. Cosecant is negative 2 means that sine is negative 1/2. So again, I drew where I have sine is a half, which is at things with 6 in the denominator. And the negative ones are 7 pi over 6 and 11 pi over 6. And you need intervals of 2 pi, so multiples of 2 pi can be added or subtracted. K could be negative, remember. Cotangent, now really cotangent and tangent, since it's negative 1, you didn't have to rewrite it, but I did. So tangent is equal to negative 1. It's equal to plus or minus 1 everywhere you have 4 in the denominator. And it's negative at 3 pi over 4 and 7 pi over 4. Because here, sine is positive, cosine is negative. Here, cosine is positive, sine is negative. So it's 3 pi over 4 plus 2 pi k, or 7 pi over 4 plus 2 pi k. But since these two happen to be exactly pi units apart, you can simplify this and just write it as 3 pi over 4 plus integer multiples of pi. It doesn't have to be 2 pi. Sometimes you get lucky that way. Okay, let's practice factoring. Factoring works just the same with trig functions as it does with variables. So if we had 9 minus x squared That's the difference of two squares. So we would write 3 minus x times 3 plus x. So if we have 9 minus tangent squared, and remember that 2 right there is the same thing as big set of parentheses squared. So this is the same as 3 minus the tangent of x times 3 plus the tangent of x. That's part A. Part B, I have sine cubed of x minus sine squared of x. Well, if we had x cubed minus x squared, we would know we could factor x squared out. Works the same with sine. So this is sine squared of x times the sine of x minus 1. Same with cosine, except we can only factor out one cosine in this case. So we have cosine cubed of x minus cosine. The biggest exponent here is a 1, so I can only factor out cosine. And then I have cosine squared of x minus 1. And then I look at that and I think, oh boy, that's a difference of two squares, just like 9 minus x squared is. So I can write this as cosine of x times cosine of x minus 1 times cosine of x plus 1. So you have to keep factoring until you can't factor anymore. And there's the pretty answers. So, solving trig equations using algebra. Look for a pattern that suggests an algebraic property, such as difference of squares or any other factoring opportunity. Substitute trig expressions with a single variable, such as u or x. You don't have to do that. We can rewrite it and just solve it like it's a polynomial to make it simpler. Solve the equation the same way an algebraic equation would be solved, and then substitute your trig function back and solve for the angle. So, example 3, solution 1. Okay, so we want to determine the solutions on 0 to 2 pi and all of the solutions of cotangent of x times sine squared minus cotangent of x equals 0. So let's write that down. This is example 3. I think I got my slides out of order. I think I should have had just the problem written down first. Cotangent of x times sine squared of x minus cotangent of x is equal to 0. So I'm going to treat these as polynomials. I really want them to look simpler. So I'm going to let u be equal to the cotangent of x and v equal the sine of x. Then I have u times v squared minus u is equal to 0. And that's something we know how to solve because it just has plain friendly u's and v's in it instead of scary trig functions. I'll factor a u out. It leaves me with v squared minus 1. And then I'll factor v squared minus 1 as v minus 1 times v plus 1. Then I would use my zero factor property that says u is equal to 0, v minus 1 is equal to 0, or v plus 1 is equal to 0. So v could be equal to 1, v could be equal to minus 1. Now I go back and I replace my u with cotangent of x, Cotangent of x is equal to 0. I replace v with sine of x. Sine of x is equal to 1. Sine of x is minus 1. So I'll start thinking about my unit circle. Cotangent is cosine of x over sine of x. Well, a fraction is equal to 0 when its numerator is equal to 0. So cosine is equal to 0 at pi over 2 and 3 pi over 2. Sine of x equals 1 at pi over 2, and sine of x is negative 1 at 3 pi over 2. So I got some overlap here. I really just got two answers on the interval from 0 to 2 pi. X equals pi over 2 or 3 pi over 2. And they happen to be just pi units apart. So instead of writing two separate expressions for all the solutions, I could just write pi over 2 plus pi k. So pi over 2 plus 2 pi k and 3 pi over 2 plus 2 pi k. I can combine into pi over 2 plus pi k. And there's the pretty answer. There's the pretty answer for that. Okay, let's look at example 4. We want to determine the solutions on the unit circle and all the solutions of this equation, and it looks kind of like a quadratic equation. So I'm going to do some substituting, and then I can just treat it like a quadratic equation. So I have 2 cosine squared x minus 3 cosine x equals minus 1. So I'm going to let u be equal to the cosine of x. I have 2u squared minus 3u, and I'm going to go ahead and add 1 to each side, because I know I have to get everybody on one side to solve a quadratic. I'm going to factor this by guessing and checking because it's really easy. There's only one way I can get to u squared. I got to have 2u, I got to have a u. 1 and 1. And it's a positive 1, so I will need a negative times a negative to get me a positive. And my middle term would be minus 1u minus 2u's, which would give me my minus 3u, which is exactly what I need. So 2u minus 1 is equal to 0. So 2u is a half. 2u is 1. I was doing arithmetic in my head. So u is a half, or u minus 1 is 0, so u is 1. Now I bring cosine back. Cosine of x is a half. Well, I know cosine is a half when I have 3's in the denominator under my pi. So, and it's positive at pi over 3. In quadrant number 1, and then in quadrant number 4, not quadrant number 3, it would be 5 pi over 3. And cosine of x is equal to 1. Only looking for answers on the interval from 0 to 2 pi, then x is equal to 0. So all my solutions, I would have pi over 3 plus 2 pi k, 5 pi over 3 plus 2 pi k, and 2 pi k, because 0 plus 2 pi k is just 2 pi k. Let's look at the pretty answers. There we go. Cosine. Cosine, that is wrong. Yeah, I will fix that. You will never see that because I'm going to fix it before I post this PowerPoint. Okay, practice, then we'll come back and compare answers. Oh, are you talking about? What typo? Is cosine of x equals 1? X is equal to 0. I have it right. I fixed it. Okay, let's look at these practice problems. We wanted to determine the solutions on 0 to 2 pi, which you do to begin with, and then you find all the solutions. So we started with 2 sine squared theta minus 1 equals 0. Now this one I did a slightly different technique than the zero factor property. And you can do this if you just have one squared thing. Since I just had 2u squared, because I'll let u be equal to sine theta, then 2u is equal to 1, so u squared is a half, but you have to remember the plus or minus. So u is equal to plus or minus the square root of 1/2, and become familiar with the fact that the square root of 1/2, well, that's 1 over the square root of 2. Rationalize the denominator, and you get square root of 2 over 2. So that is plus or minus square root of 2 over 2, which is everything that has 4 in the denominator. And that one we can even make it simpler. It's just pi over 4 plus pi over 2k, because every time we get 1/4 of the way around the unit circle, we get another answer. Part B, we had secant and sine. So I'll let u be secant and v be sine. So uv minus 2v is 0. I factored out a v. So v is 0, or u minus 2 is 0. If v is equal to 0, sine is 0 at 0 and pi. U minus 2, or u is equal to 2, secant is 2, which means cosine is a half, which means 3 in the denominator, positive cosine in quadrants 1 and 4. And then all the solutions, pi k, 3/2 plus 2 pi k, 5 pi over 3 plus 2 pi k. Okay, this one we had sines and cosines. So this one we have 4 terms, and like I tell the algebra students, if you got 4 terms, your only hope will be factor by grouping. Help me factoring by grouping, you're my only hope. So I'll let u be sine, v be cosine. So 2uv minus u plus 2v minus 1. And luckily, factoring by grouping worked. I looked at my first little partnership here. I had a common term of u. I look at my second partnership. There's no common term, no common factor, but it happens to look exactly like what's in the parentheses. So I just had pretended to factor a 1 out just so I could have parentheses around it. And it makes it really obvious that it's u plus 1 times 2v minus 1. So u is negative 1, or v is 1/2. But u is sine. Sine is negative 1 at the bottom of the unit circle. Cosine is 1/2. Hey, we just solved that. We don't need to talk about that again. And then all of the answers, we just add multiples of 2 pi k to everything. D, we have just tangents. So I'll let u be equal to tangent. But I noticed here I have tangent of x and I have tangent of minus x. So before I started my substituting, I had to take advantage of the even odd identities that tangent of negative x is the negative of the tangent of x. So you can't forget those trig identities. Then I write it as u squared. I added 2u to each side. I added 1 to each side. And when you factor that, you end up with u plus 1 squared. So you only get one little equation to solve. U equals minus 1. So tangent is equal to minus 1 at 3 pi over 4 and 7 pi over 4. So only halfway around the unit circle until you get a new answer. You can do these things. They're fun.